In this video, we will be going over 4 different types of orbital shapes and more characteristics about the orbits themselves. So we will be covering circles, ellipses, parabolas, and hyperbolas. And then we're going to compare the energy and eccentricity in each type of those 4 orbits. The first thing we have to cover is the conic section. The orbits I just listed, you can see, are in these 2 diagrams: hyperbola, parabola, ellipse, and circle. Over here, you can see the shapes of the orbit. So a circle, we all know, it's a perfect circle where every single point is the same distance away from the center. An ellipse is a little different. It looks more like an oval or an egg, and we'll get to how that shape is defined in a bit. Then there's a parabola that swoops in like this. Then there's a hyperbola, which is very similar, just a little wider. Now, why is it called the conic section? Let's look at this diagram. If you take a cone and you look at some cross sections, like if you cut the cone from here, you'll get a circle. If you cut the cone from here, you'll get an ellipse. If you cut it from here, you'll get a parabola. And if you cut it straight down, you'll get a hyperbola. You may have seen this in your math class or in a physics classroom, but the conic section is very special because any object in space can fit within one of these types of orbits. Let's go a little deeper into these shapes. First, let's start off with circles. Circles are the easiest to work with. There's a center in the middle, and this can be a sun or a planet. And then there's an object on the outside that's going to orbit at a constant velocity. Unfortunately, a perfect circle doesn't exist in outer space. However, to make our problems easier, we can approximate the elliptical shapes of maybe the orbit of a planet to be a perfect circle to make the math we're doing a lot easier because of the constant altitude and the constant velocity. So although perfect circles do not exist in outer space, we can get a very good estimate by using them. An example of this type of problem could be if there's a sun at the middle, and then there's a distance, maybe a distance r, and then we have another planet over here. And the planet is orbiting. Now let's move on to ellipses. So the way an ellipse is drawn is you have these 2 points that are called the foci of an ellipse, and every other point on the ellipse is drawn such that the sum of the 2 distances, like maybe this distance and this distance, or if we take another point, let's say this point, if we add this distance and this distance, they'll always be the same. On the screen right now, you can see a demonstration of how a perfect ellipse can be drawn just at home with a piece of cardboard, rope, and 2 push pins. The length of the rope can't change, right? But if we trace the rope around the 2 pins, we get a perfect ellipse. And this is just a good visual that shows clearly that the distances, or the sum of the distances between the 2 foci and any point on the ellipse is always constant. This is the definition of an ellipse. Now, you can see that there's 2 centers here, but if an object is, let's say, orbiting around the sun, where would the sun go? So the sun could just be put anywhere. Let's say this is the sun right here. Let's call that the sun. And this would just stay blank. So the sun would always be placed at one of the 2 foci. It doesn't matter which one. And then we could have an object that's just orbiting around. This could be any planet. So before, when we had a circle, this circle that we're using is basically approximating an ellipse. Planets actually orbit in ellipses. They don't orbit in perfect circles. They swing around the sun and then go back, swing around the sun and go back. So some key things to note is that the velocity of a planet is fastest when it's near the sun, and it's smallest when it's furthest away from the sun. So as the planet gets closer to the sun, it moves faster, and as it moves further away from the sun, because you can see that this distance is clearly smaller than this distance, the velocity decreases. If this is the center of the ellipse, we can draw a straight line throughout. This portion is called the semi-major axis, and we often use the variable a to write that. And it's semi because this is half the way across the ellipse. The entire major axis is 2a, where you would take this as well, and you'd get a total of 2a. But usually we define a only as the semi-major axis rather than the entire major axis. Similarly, we have something going along the vertical, right? We're going to have this called the semi-minor axis. So we have a semi-minor axis, where the minor axis is usually less than the major axis. Now we also have this distance from the sun to the exact center of the ellipse, and we call this c. The formula we use to connect A, B, and C is, I'll write it over here, A squared equals B squared plus C squared. It's just like Pythagorean theorem. Just remember that it's not A squared plus B squared equals C squared. And our equal sign comes between the A and the B here because of the way we defined it. The conventions are holding this as A, this as B, and this is the C. Eccentricity, which is something we're going to compare more at the end of the video. This is basically how stretched an orbit is. A circle has an eccentricity of 0 because it's not stretched at all. It's a perfect circle. Ellipses have a greater eccentricity. It's usually between 0 to 1, which is just talking about how stretched it is, and that's noted as E equals C divided by A. While we're defining ellipses, there's two more very important points that we should cover. The point closest to whatever the object is rotating around, in this case we have the sun, is going to be called the perigee, and the point furthest away is called the apogee. So if we have a planet around the sun, when the planet is closest to the sun, we'll call that perigee, or furthest from the sun would be apogee. When we're specifically dealing about the sun, we can sometimes call that perihelion and aphelion. But in general, for any type of orbit, they're called perigee and apogee. Now, I mentioned before how the eccentricity can help us do some math. There's formulas that we have for the apogee and perigee. So we can find, if we know the semi-major axis, which is A, and we know the eccentricity, what we can do is we can figure out how far the apogee or perigee is from maybe the sun or whatever else is in the center. And by center, I don't mean right in the center. I mean in one of the foci. This is going to be perigee equals semi-major axis times 1 minus E, and apogee is semi-major axis times 1 plus eccentricity. These two formulas can help define very important characteristics and locations of an elliptical orbit. Elliptical orbits is a very important topic, and we'll go much deeper in these in the next couple of videos as well. But for now, let's move on to parabolas and hyperbolas. Parabolas and hyperbolas are very similar, and they both go like this. Let's take an example of a comet around the sun. It starts at a very far away distance. It'll speed up as it goes closer, and then it'll swoop around the sun and leave permanently. Meaning that objects that orbit in parabolas and hyperbolas, they don't really orbit, they just come visit. These two objects are very, very similar. There is a small difference between them, and it's kind of weird. Parabolic orbits theoretically stop at a distance of infinity, but I'm pretty sure parabolic orbits, just like circles, don't really exist because, again, this is theoretically, but you might still come across the term parabolic orbits. Let's start comparing the energy and eccentricity between the four now. So this is a very handy table. So we have the orbit type here. We have eccentricity, and we have the total energy. So circular orbits, their eccentricity is 0, as we mentioned earlier in the video, and their total energy is less than 0. This might not make sense right now, but we'll come back to this. Elliptical orbits are less than 1. Actually, they're between 0 and 1. And same thing, the total energy is less than 0. Parabolic orbits, their eccentricity is exactly 1, and their total energy is exactly 0. And for hyperbolic orbits, their eccentricity is greater than 1 and their total energy is greater than 0. So for the negative energies, it might seem a little weird, like how can a total energy be less than 0? Again, we'll cover this a couple videos later. I just thought it'd be good to break these up. So that's coming. But for now, with these 4 types of orbits, let's try to do an example problem. Everything we learned here should be enough to try this competition problem from 2023. So the problem's saying the orbit of some planet to its star has an eccentricity of 0.086. What is the ratio of the planet's closest distance to its star to the farthest on its orbit? So if it's a planet around a star, we pretty much know that it's an ellipse. So we have an ellipse, and then we'll have a sun over here. Now it told us that our eccentricity is 0.086. Now we want the closest distance and the furthest distance on its orbit. So what does that mean? We're basically trying to find the perigee and the apogee, or perihelion and aphelion, because this is a sun. Let's recall our formulas that we learned before. So we're gonna need these 2 formulas, right? Let me copy this and bring it over. There. So to figure out what the closest distance or the furthest distance is, we need our eccentricity, and we also need the semi-major axis. But in this problem, I don't think they gave a semi-major axis. But if you read the problem again, we'll realize that we're doing just fine. They asked for the ratio of the 2 distances, right? So when we divide them out, the semi-major axes will cancel out anyway. So let's start doing the problem. They want the closest distance, which is perigee, over the furthest distance, which is apogee. So this would equal A1 minus E to A1 plus E. Now the A's cancel out, giving us 1 minus E over 1 plus E, which is, we can plug in our value, 1 minus 0.086 over 1 plus 0.086. And with our calculator, we get 0.842. And this is our ratio, and that's the correct answer. So our answer to this problem would be A. And that's it. That's question 13 from this competition. So to review, we covered what the conic section is, giving us these 4 different shapes. We went in depth for circles, ellipses, and we had 3 formulas. We had parabolas and hyperbolas and the difference and similarities between them. And then we compared the energy and eccentricity in this chart. And we'll go deeper into the total energy, how that's being defined as negative in a future video. And then last, we went through an example problem. I'll see you in the next video. As always, thank you so much for watching. The notes that I used during this video is linked in the description for you to refer to and use in the future. And please be sure to check out the rest of the videos in this series. I'll see you in the next one.